This is your friendly neighborhood physics teacher here, and we're going to do a review over energy. So this is mainly for the people that want to do the remastering for the energy, but I think energy is going to be a big factor in your AP test, so I don't think it would be hurt to go over some concepts. So I'll do a video over the multiple choice part that we took right before spring break, and then I'll do a video over the free response as well. Once these videos are up and I get the remastery up and going, so I have the questions done. I just got to get them uploaded, and you can do the remastering for getting a better grade. And yes, that would affect your last 9 weeks grade, and anyone can do it. It can only help you, can't hurt you. So let's get it going. So the first question we have here is we have a graph. That's a force position graph. So the figure above shows a net force exerted on an object as a function of the position of the object. The object starts from rest at position x equals 0 and acquires a speed of 3 meters per second after traveling a distance of 0.09 meters. What is the mass of the object? So let's kind of see what information it is giving us. So we're going to pull out our givens, so to speak. So it gives us our initial position. So our initial position is 0. Our final position is 0.09 meters. Our velocity, this is going to be our final velocity, is 0.3. And you can say that our initial velocity would be 0, right? Because it's not moving at the beginning. And so we got that, we got that, we got that. And from the graph, we know that our net force, our final net force, is 3 newtons. So that's kind of the information we've pulled from that. But we're looking for our mass. Whoops. So we're looking for our mass. So our unknown is our mass. And of course, we want that to be in kilograms. Now, a couple of things, I gave you some hints on the test. So anytime you're going from force and position, work should pop in your head, because work equals force times distance. And a couple of things. So you're like, okay, I need to get from work because there's force. So this is your force. My pen will work. This side is your force, and this is your distance. Now, a couple of things to think about. So your force equals mass times acceleration. So that could be a way to get to get mass, right? But we don't know acceleration. So we can't use that equation because we don't know acceleration. I gave you a hint about the work energy theorem. So that's when your change of energy equals your work. Specifically, your change in kinetic energy equals your work. So that's when you can do your final minus your initial equals your work. And you can break that down even further. Your 1/2 mv final minus 1/2 mv initial equals force times distance. You can start plugging in what you got at this point in time. But you can't just go straight force times distance. The reason you can't just go straight force times distance, so you can't do that, is because you have a change in force. Your force times distance, this equation right here, only works if force is constant. So it only works if force is constant. Obviously, our force is not constant. So that's where area under the curve comes into play. So work can also equal if you're given the graph, would be area under the curve. Remember, we put curve in parentheses because it's really not a curve, it's a line, but you get the idea. So our work is going to end up being area of a triangle because this makes a triangle. So in this case, work equals 1/2 base times height, and our base in this case is 0.09, and your height was 3. You plug that into your handy-dandy calculator, and you get a 0.135 joules. So that is your work. So this would go there. And you can plug in what we have. So we have 1/2. We're looking for our mass. Our final velocity was 3 squared minus 1/2. Again, we're looking for our mass. And our initial velocity was 0 equals, and you can just plug in your 0.135. 0 times anything goes to 0. And then you can do a 3 squared, gives you 9. You can go ahead and divide that, or multiply that by 1/2, or divide it by 2, and you get a 4.5 m minus 0 equals your 0.135. So you just get 4.5 times your mass equals 0.135. You divide by your 4.5, and you get the mass to be 0.03 kilograms. So your answer, is this one right here. Now, the tricky thing about this is knowing that your force was not constant. Because a lot of people are just like, okay, 3 times 0.9, right, and keep going. Nope, your force is not constant. And then also trying to get to that mass. A lot of people want to do that force equals mass times acceleration, but we don't know what the acceleration is. And there's no way, we don't have enough information to figure out what the acceleration is. So don't forget that your work equals your change in kinetic energy. The key thing is you have to pay attention is your force is constant. If it's giving you a graph, your force isn't constant. So that's when you have to do the area under the curve. So that's our first question. Second question. A crate is on a horizontal frictional surface. A force of magnitude F is exerted on the crate at an angle theta to the horizontal, as shown in the figure, causing the crate to slide to the right. The surface exerts a normal force of magnitude Fn newtons on the crate. While F is kept constant, the angle theta is now doubled, but is still less than 90 degrees. Assuming the crate remains in a contact with the surface, as the crate slides a distance d, how does the new gain in kinetic energy compare to the change in kinetic energy? So basically, you're trying to compare the two kinetic energies is what you were trying to do with this equation. So or this situation. So you have one situation, and then you have another situation, and it says that your theta is bigger. So it's kind of like going like that. And so this would be like theta 1. This is theta 2. Your force stays the same. You're just increasing your theta. So you have to think about it. If you break it down into your force in the x and force in the y, force in the y, force in the x, hopefully you see that your force in the x1 and force in the x2, force x1 is going to be bigger than your force x2 because you have more, and that being said, your force y1 is going to be less than your force y2 because it's being pulled more up. So since you have less force in the x direction, and the x direction is what's making it move, so if you're looking at your work, so work equaling your force times distance, this force, remember, has to be parallel to the motion. So the one that's parallel, so if it's moving this way, the one that's parallel to the motion is your x. So if your force in the x direction decreases, that means your work is going to decrease because it's a direct relationship. It's a direct relationship. So your change in so it says, as the crate slides a distance d, how does the new gain in kinetic energy compare to the change in kinetic energy? Think about the force components and how they affect the motion. So we already talked about the force components, how they affect the motion. So going from this one to this one, it's going to actually be less work to pull less work in the x direction to pull the block up versus pulling it more straight. That's why we invented ramps and stuff. And therefore, since your work equals your change in kinetic energy, so if your work decreases, so your change in kinetic energy, so you're thinking about 1/2 mv squared, so your mass stays the same because we're still doing the same block, so your mass stays the same, but your velocity is going to end up decreasing. Also, so your velocity is going to have to end up decreasing also. So yeah, so I don't like the way this one's worded, but there's the concept behind it. We're going to ignore, I think I ended up throwing this one out because of the wording. So we're going to ignore the wording, but kind of that's the concept. There we go. So to analyze the characteristics and performance of the brakes on a 1,500 kilogram car, researchers collected data shown in the table above. It shows the car's speed when the brakes are first applied and the corresponding braking distance required to stop the car. The magnitude of the average braking force on the car is most nearly. So again, I gave you the reference of the work energy theorem. So the key thing here, though, it says average. So we need to take the average of the speed. So to get average, you add them up. So you do 10 plus 20 plus 30, and you get a 60. But to get an average, you'd have to divide that by 3, and you get 20. And you're going to do the same thing to the distance. You're going to do 6.1 plus 23.9 plus 53.5 and divide that by 3, and you get 27.83 continuous, and so this was 8 divided by 3. So there, so we have our speed is now 20 meters per second, and we have our distance is now 27.83 meters. So we took the average of them. So we want the magnitude of the average braking force on the car is most nearly. So again, you're looking at your work energy theorem. Magnitude just means numbers, so we don't have to worry about direction. So we know that our work energy theorem, specifically our kinetic energy, so that would be our 1/2 m v squared minus 1/2 mv naught squared equals force times distance. And we are looking for our force. And this is the average, the speed that it's saying right here is when the brakes are first applied. So this would be our initial, our final, because it's coming to a stop. So this is our initial. So our final velocity would end up being 0 because it's coming to a stop. So 1/2 our mass is given to us in the problem. So it'd be 1500, 0 squared minus 1/2, 1520 squared equals, we're looking for our force, and we have our distance to be 27.83. That just goes to 0, so we get a negative, and it would just be 1500 squared divided by 2. How many zeros? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 equals force times 27. That should be 3, not a 2. And you just divide. I think what caught a lot of people on this one is the average. They didn't take the average. And you get a negative 873. So you get a negative that, but it didn't say worry about the negative. It just said just do magnitude. So the closest to that was your 12. It's probably just how you rounded. So that's why you give a roundabout, and that will be our closest answer. And again, it's probably just some rounding issues I had. Instead of me taking the whole entire numbers, I rounded. So there you go. So the next one, we have a student is asked to determine the work done on a block of wood when the block is pulled horizontally with an attached string. The student is supplied with a spring scale, a stopwatch, and a meter stick. Which of the following graphical analysis techniques will allow a student to determine the work done on the block by the string? So kind of give you an idea of what we're looking at here. Just a block with a string. Now on the string we have a spring scale. Basically it's a spring that tells you how much force. So it tells you how much force you're pulling it by. And then of course your stopwatch tells you time. And then your meter stick tells you distance. And you're trying to, again, calculate for work done. So you're seeing what you need to graph to figure out work done. Hopefully you've seen our graphs a few times. So if you do force times distance, and then you do, and then of course, if you do area under the curve, so that gives you that one. So graphing force as a function of distance and calculating the slope, remember that doesn't get you anything. That just gives you force rise over run. That gives force divided by distance, and your work is force times distance. So that doesn't work. Your slope doesn't work. Force as time, now that we know momentum, and you're graphing force over time, and you take the area of that, you're actually solving for force times time, actually gives you your change momentum. So that was, if you're looking for your change momentum, that's actually a good graph to do, but we weren't. And then if you just do force divided by time, do the slope, that doesn't get you anything. So they were trying to be tricky in there and putting the force as a function of time in there, because that is a thing you have to solve for momentum. We just, at this point in time, hadn't talked about it now, but we have now. So next question. We have the pendulum shown as a figure above reaches a maximum height h above the equilibrium position as it oscillates. Assuming friction and air resistance, I don't know why it says Sir resistance, I'm talented like that, air resistance is negligible. Which of the following is true about the total energy of the Earth pendulum system as the pendulum oscillates? So no air resistance, aka no friction. So I've given you, it's the Earth pendulum system. So you have to think about Earth, it does play a part in it. So why is it important to have the Earth play a part in it? Hopefully you realize because it's gravity that's pulling it down. So if you think about your energy, so up here we have gravitational potential energy. Down here we have kinetic energy. And since there's no air resistance, there's no friction, that means that your potential at the top equals your kinetic at the bottom. And that is true because of your conservation of energy. Conservation of energy. That's how you're able to do that. It's through the conservation of energy. You have potential at the top equals your kinetic at the bottom. And it's an even transfer through. So, which of the following is a true about total energy of the Earth pendulum system as the pendulum oscillates? So let's think about it. So it is at a maximum when the pendulum is at its lowest point. So it's asking, it is at a maximum. So it's saying that the total energy is at a maximum. So when it's at its lowest point, potentially it is at a maximum when the pendulum is at its highest point. It is constant throughout the pendulum's motion. It is at a minimum when the pendulum is somewhere between the lowest. Now, the key thing here we have to watch out is it's talking about its total energy. Total energy. Remember, your total energy equals your potential plus your kinetic. Is your potential plus your kinetic at any point here. So if we're doing total energy at the top, our total energy at the top is just potential energy because we have no kinetic energy. If we're doing total energy at the bottom, it's just going to be kinetic energy. So that's why you can get the potential at the top equals your potential at the top equals your kinetic at the bottom. And so your total energy never changes. It stays constant. That's where the conservation of energy statement comes into play. And the reason it was so important to say that it's a Earth pendulum system is because it's not, the ball isn't losing energy to the Earth. The Earth is playing that part. It's causing it to move. Now, if we did just said a pendulum system, didn't throw the Earth in there, then that's when you have to sit there and decide, okay, so it's losing energy to the Earth and stuff and all that fun stuff. But as long as it has an Earth pendulum system, it stays constant. Next question. A cart is constrained to move along a straight line. A varying net force along the distance of motion is exerted on the cart. So is our force constant? No. So we know that work equals force times distance can't be done because our force is not constant. As it says there, it's a varying net force. The cart's velocity v as a function of time is shown in the graph above. The 5 labeled points divide the graph into 4 sections. During some part of the motion, the work done on the cart is negative. What feature of the motion indicates this? So again, you have to think about your work energy theorem. So our work equals our change in kinetic energy. So for our change in kinetic energy to be negative, because it's our final, so if we think about kinetic energy, our final minus our initial. For it to be negative, that means our initial velocity has to be bigger. So our initial velocity has to be bigger than our final velocity. So in what situation that our initial velocity is bigger than our final velocity? So let's just take it from point to point. So from here, it's going from 0 to 8. So nope, that doesn't work. So it's not that area. It's staying constant, so that's not that area. So our velocity is going from 8 to 0, so that's a possibility. Then it's going from 0 to 4, so it's not that. So where we have a negative work is in this area right here. So what's happening in that area right there? That's what we have to think about. What's happening? So speed. So why is that a negative work? And it's because you have your slope. Your slope's negative. So if remember, for velocity time, so your slope for velocity time is your acceleration. So anytime you have your acceleration, so anytime you have a negative slope, anytime you have a negative slope, you're going to end up getting a negative work. And I messed up right here. This is also negative work. Because yes, your initial is 0, but you still have a negative slope. So you're doing negative work because your acceleration is negative. So that's why your answer is the acceleration is negative and not speed is decreasing. So anytime you have a negative acceleration, you're going to end up having negative work. And if you think about it, it's also because, your force equals, I love it when your pen just stops working, equals mass times acceleration. So if you get mass times acceleration times distance, you get that your acceleration is negative. Oh, Lord have mercy. Come on. So you get that your mass minus your acceleration. I have no idea what's going on all of a sudden. You get that negative work also. Let's go to the next question. So an object with mass m is suspended from at rest from a spring with a spring constant of 200 Newton meters. The length of the spring is 5.0 centimeters long. Then its unstretched length is L, as shown above. A person then exerts a force on the object and stretches the spring additional 5 centimeters. What is the total energy stored in the spring as the new stretch length? Don't forget to convert. So we have we're looking for the total energy stored in the spring. So we're just looking at our spring is 1/2 k x squared. It gives us our spring constant right there, so that is our k. And then the total is the total energy stored. And then and we have to convert, so don't forget to convert. So we have our 5 centimeters. If we think about kiss her daily because divorce costs money, and we're going to convert So we're starting at centimeters and we need to go to meters. So we're going to go 1, 2. So we're going to go to 1, 2. So we get that equals 0.05 meters. And the trick here is where equilibrium is, because it says that the length of the spring is longer when it's unstretched length, and then the person exerts an extra force to stretch it. So this right here, it's at equilibrium. So stretching that extra 5, so your x is just 5. So you just do your 1/2, 200, make sure you do your converted version, and you get that your spring potential of the spring is just 0.25 joules. I think what a lot of people here is they did the 5 plus 5, and because they think it's the total stretch. But remember your x, and this is just from equilibrium. It's your stretch from equilibrium. 3 identical blocks each take a different path from a height to the ground. Block A is released from rest and falls vertically. Block B is released from rest and slides down a frictionless incline. Block C is projected horizontally with an initial speed v. Which block has the greatest speed just before it hits the ground? Hint: think overall speed, not just components. So what I was trying to do with that hint is if it's going at an angle, you have to think about your x and y components. So like this one only has velocity in the y. This one, if we, change up our frame of reference, only has velocity in the x. This one has velocity at the end, right? At the end has velocity y and velocity in the x. So this one has both. So you could sit there and figure out each one of these. You really could. The only one you really can't, because you don't know what your initial velocity is here, but if you sit there and like for A, if you really want to do the math here, so and it's sit there at A, you could realize that your final velocity equals initial velocity plus AT. If you knew time, you could sit there and figure it out. And since it's the same exact height, you know that it's going to be pretty much the exact same time, at least for your A and your C. Don't know why it's not erasing. I'm trying to erase it. There we go. Just not wanting to work for me today. And so the key thing is you didn't have to sit there and do the math for anything. You could realize that the answer is C because it involves your y and your x. This one just involves x, this just involves a y. This is the one that involves your x and your y. So of course your overall speed is going to be greater because you're having 2 components versus just the 1 component. One more question, I believe. 2 more questions. So a 5-kilogram athlete running at speed v grabs a light rope and hangs from a 10-meter high platform and swings to a maximum of 1.8 meters above the ground. Later, a 100-kilogram athlete runs at the same speed, grabs a similar rope hanging from 5 meters high platform. What is the maximum height to which the 100-kilogram athlete swings? So you have to think about conservation of energy, and it is a closed system. So your velocities are the same. Your velocities are the same. So you have to think about, so let's focus on this one right here. So if we have our kinetic at the bottom equals our potential at the top. So we have 1/2 50 v squared equals 50 9.8, and it says it does a maximum of 1.9. So So we can sit there and figure out the velocity. So you just kind of simplify, so you get 25v squared equals your 88 to divide. So you get v squared equals your 35.28. Get a square root. So square root your answer, and you get your velocity 5.94 meters per second. Since it says it's the exact same speed, again, you can just move over and do the exact same equation. So your kinetic at the bottom equals your potential at the top. So you have 1/2 mv squared equals mgh, so 1/2 mass now is 100, but it's still moving at 5.94, so 4, there we go, equals 100, 9.8, and you're looking for your height. So you get 5.94 squared times 100 divided by 2 gives you this answer over here. And then 100 times 9.8 gives you that. You divide. So you get that the height of the bigger guy and shorter string is, oh, look at that, the same. I wonder why. Nope. So you get the same. I wonder why it's the same. If you look at your equation, what can you happen to do to your two masses? They cancel out. So everything stays the same. It just cancels out. So that's why it's able to be the same. So you didn't necessarily have to do any of this math. You could just be, it's the same. If velocity is the same, and then your height has got to be the same. It doesn't matter how high up the platform is, because you're only allowed to put that much energy into it. So there you go. So our last question. This is our last question. And so we have two objects, both initially at rest, are released from the same height and follow the paths shown below. Each object will have the greater final, which object will have the greater final speed at the finish line? Hint, conservation of energy. We kind of did an example of this when we talked about motion on the in the slides. So there's an example of this. So they start out at the same height. So same height. So if we call this object 1 and object 2. So for object 1, we have your gravitational potential, which gets converted into kinetic, and it stays at that kinetic all the way through. R2 has some gravitational potential that gets converted to kinetic, but then it gets converted into a little bit more kinetic because it goes a little bit more the same, but then that kinetic gets converted back to a little bit of our gravitation. So whatever kinetic it gained, it went back to a little bit towards our gravitation. So at the finish line, the two objects have the same speed, but it doesn't ask you which one finishes first. So which one would finish first? Hopefully you said number 2. So number 2 will end up finishing first. And it's because it gets that gain in speed as it goes down that little extra 1 meter. Because the lower it is, the more kinetic energy it can gain. So that little extra spin, and it gains speed. So even though it's at the same speed, therefore same energy, when it crosses the finish line, 2 will cross the finish line first. So there we go. So that is our multiple choice part of the review. I will get this uploaded and I will do the free response. And if you need any help, don't be afraid to ask. Have a wonderful day. Bye.